all for coming to the talk. I don't know who's online, but everybody who came in virtually, thank you for coming in. And I appreciate the invitation to speak, and especially thanks go to the organizers for putting the meeting together. So I want to talk about computability and computability-theoretic and set-theoretic aspects of Hausdorff Dimension. Before that, though, I want to apologize in some way, well, to the people who've heard versions of this talk before. I've tried to for this talk add a little bit, and I hope clarify the things that I've said before that weren't quite so well articulated. With that in mind, though, I want to sort of, as a preamble, I was told by a Japanese colleague once that in Japanese culture, there are 2 times in a person's life when that person is free to do what they want and say what they want. Those 2 times are when the person is very young, and the age is typically 4 to 5, after which you're no longer free. Or when the person is old. Once you're old, you're free again to without consequence, to do what you want and to say what you want. Now, I recently made public, I'm 68. I'm 68. So, but I recently, yeah, well, I am going to decide. I recently made public my intention to retire, which I will do officially a year from now. So I'm taking that as a watershed, and now I feel free to say and do what I feel like. I think that when I told people I was going to retire, I got some interesting reactions from people. I think half of the people thought I was already retired. The other half, I don't know if they even thought I was still alive. So some mix of that. But the typical question is, what are you going to do? I don't know what kind of, so I tried to be honest in my answers, to that. I don't know what people were expecting, though, when they asked that question. But what are you going to do now that you're retired? And what do they think? I'm going to wear the bottoms of my trousers rolled, walk upon the beach, listen to the mermaids sing, each to each. That's what they think. I'm okay. It's okay with me if that's what you think, because that is exactly what I'm going to do. In fact, if I weren't here in person, that's what I would be doing. So let's yes.
Since you're free to say what you want to say.
I didn't say you were free.
No,
Since
I know I'm not free. I'm still not old enough. I'll be 68 in a few years, so then I look forward to that. But what have you missed saying that you?
What's that?
What have you missed saying now?
Well, that's what I'm going to give a talk on. Yeah. So now where was I now? You threw me off. Yeah. So I guess now that I am free, whatever I am, whatever I'm going to be, I'm just going to flaunt it. That's be who you are and be proud of it, and like wear it on your sleeve. That's my plan. Okay, so now let's get focused here. Let's all be computability, set theoretic, mathematical logicians, and let's talk about a Hausdorff dimension. Okay. So what I should say is we're going to I'm going to look at various ingredients from mathematical logic, right, and see how those ingredients inform us about issues in geometric measure theory. Okay. And except when I cite the work. Otherwise, this is all joint work with Jan Reimann. The things that this particular collection of projects leverage out of logic. So what to expect? What are the ingredients from logic? We're going to be talking about analytic and co-analytic sets. So there's a way to, co-analytic is the complement of an analytic set, and a way to think about it as a logician. What is a co-analytic set? Co-analytic set is determined by a real parameter P, and X, the co-analytic set, A is the co-analytic set, X is in A, is something that's uniformly sigma 1 definable relative to the parameter P inside L omega 1 of XP, the least, what you can construct from X and P up to heights, the least ordinal that's not recursive in the joint of X and P. So sigma 1 over that set theoretic structure is the same as pi 1 relative to P, and that's what that's our view of a co-analytic set. The nice thing about looking at this way of formulating being co-analytic is that you can think about what's happening inside L of omega 1 X, right? And use that to define properties about X, and you end up with something that's co-analytic. And if V equals L, every real belongs to an initial segment of L inside the constructible universe. And for some reals, they can capture interesting features. Okay, secondly, the second ingredient is some business about forcing and set theory of the continuums. We'll pull in a little bit about that kind of thing. Generic models and what can be true inside generic models. And finally, the semi-recently uncovered, which we've all heard about quite recently, connections between algorithmic randomness and Hausdorff dimension. And sorry everybody about the semi recently, but recently has a very short shelf life in math. Semi recently is still pretty close. And finally, we're not gonna really get into any details here, but I want to cite some interesting work and also some quite interesting questions that involve what happens for the structure of the subsets of the reals under determinacy or large cardinal properties. Okay, so the main object that I want to talk about is the subject of gauge functions and general Hausdorff dimension. So a gauge function is a function from the positive reals to the positive reals. It must be continuous, increasing in the argument, and the limit as h goes to 0 from the positive has to be 0. Examples, the power functions. If I have a positive exponent, then the power function h of t is t to the s is a gauge function. So we've seen this definition for Hausdorff dimension. It's the same logical form for a gauge function. If you have a gauge function h, then you can define the h outer measure of a set A to be the limit as, let me see if I can use this thing. I can use it. Okay, so this is sort of the limit as you look at a scale. Scale goes to small of the inf of the h description of the sizes of the basic open sets that go into a covering of A. Okay, so it's the inf over all the open covers of the sum of the h measures of the sizes of the constituents in the open cover. Okay. H is a power function. This, what you usually write as hs. hh for this function is the usual s-dimensional Hausdorff outer measure. Why do you use gauge functions? Right? Well, that's the answer is that that's all they give a more finely graded calibration of measure, therefore a more finely calibrated view of dimension than just talking about the power functions. There's distinctions that you can make using some gauge functions that you can't make just using the power functions. For example, right, just the Hausdorff dimension is a way to assign size to sets that have Lebesgue measure 0. And there's bigger dimension or smaller dimension. How do you decide, how do you assign size to sets that have Hausdorff dimension 0? Hausdorff dimension is obliterating those sets, just like Lebesgue measures obliterating the sets, the null sets, right, that Hausdorff dimension measures. If you want to look at something that's thinner, that has Hausdorff dimension 0, then you have to move to a more finely graded notion of dimension. And there's I recommend this book, it's fairly recent, about aspects of Brownian motion. There's interesting aspects of Brownian motion that you can't calibrate using Hausdorff dimension, but they have very precise and interesting distinctions that you can make. And this is a really nice treatment of that material. It's a monograph, and it's a very nice treatment of that material. Okay, so among the gauge functions, you can order them. Okay, so h is less than g means that the limit as t goes to 0 from the positive, so the limit as t shrinks down to 0 of g of t divided by h of t is 0. Okay, so a way to read this is that if you have positive hg outer measure, right, that indicates a greater fullness than positive HH outer measure. So if G is going to 0 faster, to have positive measure for G means you have to be bigger. Okay, so this order is chose to reflect an aspect of dimension. Okay. Just like dimension 1, right, is greater than dimension 1/2. Right? 1 goes to 0 faster. I mean, t goes to 0 faster than t to the 1/2, or like in this example. Okay, Hausdorff dimension is of a set is the number d such that to the left of d, the outer measure is equal to infinity, and to the right of d, the outer measure is equal to 0. Okay, so this is the definition that we've seen previously. We'll get to gauge functions. We'll come back to gauge functions. For this slide, I'm just talking about Hausdorff dimension. Okay, so I've been thinking about Hausdorff dimension for a long time, just as subsets of the line. But when you start to think of it in like subsets of the plane or larger spaces, then it's sort of clear why geometry would consider it, right? If you have a line in the plane or a line through three-dimensional space, right? It has in the plane, it has 0 area, right? But it has extent. Right? So how do you measure the extent of a curve, of a space-filling curve, of a nice smooth curve? How do you distinguish between those things? And that's where this kind of dimension comes in. It's valuable in that way. Okay, so a line has dimension 1, even though it has measure viewed as a subset of the plane equal to 0. And then there's other things. The Cantor middle third set has dimension log 2 over log 3, and lots of these sort of ways of forming Cantor-like sets, self-similar fractals and so on. You can figure out their dimensions. Okay. Now I want to recall, which we've seen, but we're going to need this. This notion of effective dimension, which we've heard a few talks about already. So the effective dimension of a point is effective dimension was defined by Jack, and then this characterization was given by Elvira. To me, this characterization of effective dimension of a point was a really cool insight, right? And kudos on the theorem, because it puts it into a language that makes it very easy for me to understand. It's familiar ingredients, right? It makes it accessible for somebody who's steeped in the tradition of computability and logic. Okay, so the effective dimension of a point X is just the lim of the ratio of the complexity of the first L bits divided by L. And the Hausdorff dimension can be correlated, expressed in these terms, which makes Hausdorff dimension of an arbitrary set accessible to me as well. It's the inf over all B of the supremum over all X of the effective dimension relative to B of the elements X and A. Okay, so you look at now this I think is a superb application of conceptual application of the existence of universal sets in computability theory, because you can take arbitrary covers and having a cover, go back to this thing, go back to this, right? And it's so what's happening? We're looking at arbitrary covers. Well, that's all the B's. That's an oracle. You can have an oracle for a cover, and then to say, the limit is delta goes to 0. That's taking something happens infinitely often. You can compress infinitely often, right? And how much compression? Well, that's what H is telling you. So it's and then you can put this sort of quantification over all covers. You can put that into a universal language, just talking about compression. Right? So Kolmogorov complexity is robust because there's a universal compressor, right? So it makes sense to talk about it. Anyway, it's quite a useful way to repack and express the notion. Okay, now the clarity that you have, the sort of complete analysis of how things work with Hausdorff dimension transfers, but only partially to gauge dimension. Okay, so just in case you are like me and the definitions disappear as soon as the slide changes, here's the definition again. Okay, so what are the similarities between talking about dimension G as an abstract dimension and dimension H? Okay, well, if A has finite H outer measure, okay, then and G is to the right, well then, if H gives a finite outer measure and G is to the right, then G gives a 0 measure. Okay, so if something is finite, after that, if you see at H that the outer measure is finite, after that, the set looks negligible. If H at A is not 0, right, then to the left, H of A is infinite. Okay, so if you see that H says that the thing has some extent, it has dimension, right? Then anything to the left says yes, it has a dimension. In a big sense, it's a really big set. A difference. So Besekovich. So we're going to mention a collection of results from the 50s. Besekovich showed that if H of A is 0, I mean, if the outer measure of A, according to the gauge function H, is 0, right, then there's something to the left, which also says that A gets outer measure 0. So if a set looks small in the sense of H, right, it looks small for something that's to the left of H. So there's like an underspill effect. Right? There isn't a sharp boundary at which you can't look small at a boundary where you look big ever after, or ever after to the left. Okay, so, all right, so that brings us to this. This is the thing that I want to spend most of it. Yeah, go ahead. Yeah, there is a cut, right? But you can't at the cut itself, right, have measure zero. Yeah. Yeah, we'll see some more examples. Okay, so a set is sigma finite if for H, if and only if it's a countable union of sets, each of which is finite for the gauge function H. So sigma finite set is one that you can break up into countably many pieces such that each piece looks finite. Example, right? A line in the plane is sigma finite for linear measure. Right? Or just the real line is sigma finite for Lebesgue measure, right? You can break it up into the intervals n to n plus 1. Okay? So you can take the thing that has infinite measure, and break it up into small pieces. Okay. Okay, so sets that are not sigma finite are big. If you have a set that's not sigma finite for the gauge function H, then that set looks really big for H. Okay, so the previous slide said that if A has non-zero outer measure for the gauge function H, then anything to the left says that A is infinite. Okay, that's, in fact, everything to the left says A is not sigma finite. So if the gauge function H thinks that A looks big, everything to the left of H, right, thinks that A looks gigantic. Okay, so example, how about a couple of examples of sort of reasonably naturally occurring sets and measures for which those sets are not sigma finite. Okay. All right, so if you have some intermediate dimension, then the set of things that have effective dimension D has Hausdorff dimension D's, and it is not sigma finite for HD. So this is sort of the nicest example that I guess, you could sort of think like in a tennis tournament, there are the amateur players and the professional players, right? So I'm trying to get into the amateur ranks here, but I'm not a professional. So in geometric measure theory, so it's possible that there are other really nice examples that I have not come across, but Google-enabled investigations have not brought up lots of really interesting examples of sets that have a certain dimension and are not sigma finite at that dimension. This seems to me to be the well, I'm biased by my previous experience, but this seems to be the most interesting and natural example I could find. Okay, so there's a question, right? Is there a similarly canonical example for gauge dimension? Right. So I'd like to know, is there a set, right, that we can, such that it has exactly gauge dimension H, and is not sigma finite for H? The answer, oh yeah, hint on the answer here, it's complicated. Right? So we're going to see some, well, we'll see something about that kind of question. Okay, so that's that example. This is another interesting example. This example is the set of Liouville numbers. The Liouville number is a number such that for every k, this is one way to describe it. For every k, there is a rational p over q such that the Liouville number, the distance between the Liouville number and p over q is less than 1 over q to the k. Okay, so if k is large, this p over q approximates c, right, to very excellent precision viewed in the scale of qths. Okay, so Liouville number is a number that can be very well approximated in arbitrary scales. Okay. So it's sort of like a number that can be compressed arbitrarily much. Okay, but the compression is not compression algorithmically, it's kind of linear approximation just by ratios. Okay, so the set of Liouville numbers, but yeah, has a bit of mathematical lore. The first proof that there are non-algebraic real numbers is due to Liouville prior to Cantor's diagonal argument, right? And Liouville used Liouville exhibited a number like this, the sum 1 over 10, the sum of 10 to the minus n factorial. And that sum has this property, and no algebraic number has this property. No irrational algebraic number has this property. So the Liouville numbers were the first examples of transcendental numbers. Okay, but anyway, this set, by virtue of these arbitrary instances of compression, has Hausdorff dimension 0. But if you take any gauge function, which is to the left of all the power functions, right, it gives this set a non-sigma finite measure. So it's an interesting example of something that looks big relative to every gauge function. It's a maximally large dimension 0 set. And there's a lot of similarity between this set and this kind of set. Right? And a lot of the examples that seem to come up in one way or another, these number theoretic examples were prior, in the mid-1800s, prior to this notion of effective dimension. The idea of compression and approximation by simpler things is a prior notion. But lots of the interest, there are other examples like things out of Brownian motion and so on, but many of the really interesting examples come out of the aspects of approximation. Okay, so I don't know that this is a more open-ended problem. This may be a more tractable problem. This is a more open-ended problem. Is there some way we can look at the elements of a set and see that set is not sigma finite, for a particular gauge function? Now I wanted to talk about this business of a cut, like Peter said. So I want a set A has strong dimension H, or E. I guess I used E here. E has strong dimension H means. Right? If you look at anything that's to the left of H, right, any F to the left of H has the property that the set looks to have infinite size relative to F. Okay? And to the right of H, it looks like it's trivial. Right? It's a null set. Okay, so then H is telling you, among all gauge functions, not just power functions, but among all functions, right, the exact size of E. And so that's strong dimension. Okay, and then there's a limiting case. Strong dimension 0 just means take any gauge function whatsoever, the set looks trivial for that gauge function. A good example of a set of strong dimension 0 is the empty set. Or a point, right? A single point has strong, countably many points. Those sets all have strong dimension 0. So we'll come back to those examples. Okay, another example, a line segment. Take a line segment in the plane. Right? That set has strong dimension 1. That's something to check, right? So it's not like such a restrictive definition that nothing natural satisfies it. Right? A line has strong dimension 1. So you can think of points, lines, things like that. They exhibit aspects of strong dimension. Yeah, correct. That's right. Okay, so now I cited this earlier theorem, right? And the theorem by Besekovich says that if h of a is equal to 0, there is a j to the left, such that h of a there is equal to 0. Consequently, if ha is equal to 0, if a gauge function gives a outer measure 0, then the set cannot have exact dimension H, right? Because it spills to the left. You can have sets that have Hausdorff dimension D, right? And have Hausdorff outer measure as 0. For D. Okay, so now here's, how about a set that looks large at its dimension, like we did with non-sigma finite things of Hausdorff dimension D? How about a set that looks large at its strong dimension? Okay, so Besikovich again, and later Rogers. Oh, there's a really nice book. The other place that I learned, my go-to for information about Hausdorff dimension is a really nice book by Rogers called Hausdorff Dimension. So if you're interested, that's a nice place to read about this business. If E is compact, so if you have a compact set and it's not sigma finite for the gauge function H, then there is a G. So G is to the right. G assigns larger dimension, and E is not sigma finite for G. Okay, so the kind of example that we had where we had, well, for a compact set, it can't be not sigma finite at its strong dimension if it has a strong dimension. Okay, this fact can be coupled with another one by Davies, and then later for general gauge functions. If E is analytic and it's not sigma finite for a gauge function H, then there's a compact subset of E that's not sigma finite for that same gauge function. So the non-sigma finiteness of analytic sets resides on their closed subsets, right? So the size of E, right, resides on its closed on a simple. It's supported by a closed subset. And consequently, this theorem applies to analytic sets. Right? If you have any analytic set, and it's not sigma finite at H, H is not its strong dimension. This is an interesting. Well, we'll get to a little bit more about this later. But this investigation of you have a set and it has extent, it has dimension. What does that dimension live on? What is it that's filling the set out to give it extent? Right? It's a natural thing to ask about closed sets because Lebesgue measure has the property that if you can approximate the measure of a set from within by its closed subsets. Right? So it's a natural thing to look at this kind of question, but that's not the only thing you can look for. You can look for any kind of explanation. Why is it that this set has a certain dimension? What is existing inside the set that supports its size? Like the complexity of its points. Okay, so this example that we had, the set of things that have effective dimension D, it does not have strong dimension given by the power function. There are gauge functions that dominate this, and because this set, whoops, how does this? Oh, there we go. This set is analytic, and it's not sigma finite for that function. So that's not its strong dimension. Okay. So the attempt to look to see, what kind of sets can you find, right, that look large at their strong dimension, right? There's a serious obstacle here. Okay, next. Besikovich in 63. If the CH holds, for now set theoretic ingredients pop up, there is a set E such that E has subset of the plane. It has strong linear dimension and it's not sigma finite for linear measure. Okay, that's an interesting one. Right? So it is an example of something that has strong dimension, right? And it's large at its dimension. So, but it does come from this CH business. Okay, then you can take that. I'm going to draw a picture for Besekovich's example in a second. You can take what Besekovich did here and combine it with aspects of constructibility, and you can invoke, if you want to, a theorem of Erdős, Kunin, and Molden to say that if V equals L, where the CH holds, right? But there's a much better example than this one. If V equals L, there is a pi11 set E, such that E is a subset of the plane and has strong linear dimension. It's not sigma finite for linear measure. Okay, so the Besekovich theorem and Besekovich-Davies et al. Theorem about analytic sets, right, is best possible. I mean, you can't do better. We'll see it in a second, a bit more about this. Okay, so how does the proof go? Well, what Besekovich did was use the CH to prove that there's an uncountable set, which they called is concentrated on the rationals. Concentrated on the rational means any open cover of the rationals is a cover for that set. Okay, so no matter how you cover the rational numbers by open balls, you end up covering this set too. And so that's a or maybe cover mod finite, but or mod countable. Then yeah, I think it's cover mod countable. Okay, so that's under the CH. You can prove that there exists such a thing, and then if V equals L, there's a co-analytic example. Yeah, you do a omega-1 transfinite recursion to build the set A, correct. Okay, so it's in what did we just say, right? So let's go back now. What have we got? For analytic sets, you cannot have a set that is any set that is not that any analytic set that's not sigma finite at H does not have strong dimension H. Okay. In L, there's a co-analytic set, right? Effectively described co-analytic set, which has strong dimension 1, linear, and is not sigma finite for linear Hausdorff outer measure. Okay, so co-analytic is best possible. So there are some theorems that even if you know the point to set principle, you cannot use it to go from analytic sets to all sets. Okay, there's a couple of other examples I wanted to mention in passing. This business of having that the dimension of a set is supported by its closed subsets. Right? That's called capacitability. Besekovich and Davies proved in the 50s if A is an analytic set and it has dimension D, then for every S less than D, there's a closed set contained in A such that that closed set has dimension at least S. So you can fill A in by closed subsets of arbitrarily large dimension below the dimension of A. Okay, so the dimension of A is supported by the dimensions of its closed subsets. And then you could ask, right, like in the previous thing, what about co-analytic sets? An analytic set is the continuous image of a Polish space. Right? How about the complement? Or it's a good. How about a co-analytic set, the next most complicated set? And inside L, the maximal thin pi11 set, that is the X such that X is in L omega 1 of X. X can compute the ordinal at which it's constructed. You know that. So it's that set, right, is maximum. And this is not a V equals L fact. That every thin, no uncountable closed subset, every thin pi11 set is a subset of this set. You don't need V equals L for that. It's just a fact. Okay, so that set has Hausdorff dimension 1 in L. but all of its thin, all of its closed subsets are countable, right? So it's an extreme counterexample to this kind of phenomenon, right? It has full dimension, but all of its closed subsets are countable, and they all have gauge dimension 0 for every gauge function. They're as small as possible. Yeah, so there's no closed subset there that supports the size of that thing at all. Well, compact set's closed then. So it's similar. Okay, so second example. So this is a theorem of Marstrand from 1952. Look, suppose you have an analytic subset of the plane, and you have an angle. Right? I guess I could have just gone from 0 to pi, but okay. But you have an angle, and you let P theta of E be the projection of E onto the line through the origin at the angle theta. Okay, so I have an angle theta, maybe it's like 45 degrees, and I look at the line that's 45 degrees off horizontal and take E and project it onto that line. All right, so you're looking at E from the point of view of perpendicular to the line. Right? And okay, so then Marsden proved that for analytic sets, if E has dimension greater than 1, then for almost every angle, this projection of E onto the line that has angle theta with horizontal has positive measure. Okay, so for almost every angle, right, the shadow of E is solid. Right? And then the joint work with Stahl. So I should put a asterisk on this theorem because we haven't written this proof down, but it looks good. If V equals L, then for every S between 0 and 1, there is a co-analytic set E such that E has dimension 1 plus S, right? But the dimension of its projections on every angle is at most S. Okay, so this is a set that has extent. It could have dimension 1.9 as a subset of the plane, but if you look at it at an angle, it looks like a spider web. It has very small dimension. And so you can see through it from every angle, but it has extent. And this is another one, right? But where does this come from? It comes from the analysis of pi 1, 1, right? You can look at and going through the point to set. Right? You can implement a recursion, right, by looking at x's that can compute the ordinal at which they are constructed. Right? So you look at essentially work on the master codes of L. Right? So the definability aspects of the points that are in the set determine its geometric properties. It's an interesting situation. Okay. All right, so I want to return to this. That was an aside. I want to return to this business about not sigma finites and strong dimension. Okay? So here's a connection with a set theoretic precursor. Okay, so a set is said to have strong dimension, strong measure 0, if and only if for every sequence of positive real numbers epsilon sub I, there is a sequence of open intervals O sub I, such that each OI has length at most epsilon I. So take a sequence of E is strong dimension 0. Take a sequence of numbers of positive numbers that shrink as quickly as you want them to, right? So they are, the next one is, infinitesimally small compared to its predecessor. Take any sequence you want at all, and even so, no matter what sequence you have, E can be covered by a collection of balls whose diameters are as prescribed by the sequence. Okay, so that's strong measure 0. Looks like a small set. You can cover it by these kinds of incredibly shrinking. Ant-Man could cover it, no matter how fast he shrinks. Yeah. So Borel 103 years ago. What was that? And Borel conjectured that strong measure zero, the property of having strong measure zero, meant you're countable. Countable sets have strong measure zero. Borel's conjecture was, if you have strong measure zero, you have to be countable. There are no sets, basically, no non-trivial examples of sets that are this small. Then in 28, my favorite guy, Sierpinski, proved that under CH, the Borel conjecture fails. You can build a counterexample to the Borel conjecture. Somewhat later, 50 years later, Laver, and I think that's probably where Laver rank was used. Laver, because he did this by forcing arguments using infinitely branching trees. Okay, so Laver in 76 proved that it's consistent with the axioms of set theory that the Borel conjecture is true. This is a very super interesting argument in a very particular kind of model of set theory. The first example, I believe, of a sophisticated iterated forcing in which the support was not finite. Yeah, go ahead, Joan. Oh, there's a comment in the chat.
Turn off the microphone.
Ah, okay. Did you turn off everybody else's microphone when they were speaking? Okay. All right, so that's the status with the Borel conjecture. So what's the connection for us? Well, Besekovich again, my other guy. Besekovich proved that strong dimension zero is the same as strong measure zero. So asymptotically, right, having for every gauge function outer measure zero, right, is the same as having strong measure zero. So the asymptotic property of gauge dimension. Okay, so now you can use I mean, this connection with strong dimension and strong measure, and you can get some leverage out of it. Right? Besekovich's example was to take a small set on the y-axis and put line segments across for each element of that small set, and you get an uncountable set that is not sigma finite for linear measure, but has strong linear dimension. If you just take a counterexample to the Borel conjecture, you don't need this thing that concentrates on rationals or so on. Any counterexample to the Borel conjecture would give you an example of a set that has strong linear dimension and is not sigma finite. Okay, I don't know the answer to this question. Does the Borel conjecture, which is talking about sets of Lebesgue measure zero, and saying that there are no non-trivial ones, right, that have strong measure zero, does that also extend all the way through all possible dimensions, right? That there does not exist an H and an A such that A has strong dimension H and A is not sigma finite for the outer measure corresponding to the function H. So I think the answer is yes, but it's, like I'm stumped on how to prove it. And even this fact, I don't know, this proof is quite specific to the theorem that's being proven, right? So I don't even know of a way to at arbitrary gauge function rather than asymptotic under all gauge functions formulate the question about strong dimension in terms of something else. Maybe that suggests that the answer is no, but we'll see. I hope we'll see. Okay, so the problem to overcome here is it's difficult to analyze what it means for a set to have non-sigma finite measure. Right? That's there isn't an arbitrary countable partition of the set into pieces, each of which has finite measure. Right, so that's there's an additional quantifier there that is hard to track. And so let's try to quantify that a little bit and see if we can't get some insight. So here's the case study. And, let's talk about simple sets, and I want to compare having positive measure to being non-sigma finite measure. Okay, so let's talk about closed subsets of this Cantor square, okay, and linear measure. Okay, so there's no funny business about the gauge function, right? The measure of an open ball is just its diameter, and there's no funny business about the space. So I don't know, maybe you think that space is funny, but okay. So exercise. The set of indices for pi01 for pi01 subsets of the Cantor square of non-zero linear measure is an arithmetic set, and it's because this space is compact, right? So so why is it arithmetic? Well, usually when you talk about the measure, you talk about some, a collection of possible open covers, right? That looks like a quantifier over reals, but this space is compact. All the open covers of a pi01 set can be reduced to finite. So the definition of having positive outer measure, right, is quantifiers over finite, right? So prima facie, it can be expressed arithmetically. Okay, so let's let this not sigma finite, n sigma finite, the set of indices for light phase closed subsets of the Cantor square such that C is not sigma finite for linear measure. Okay. So the analysis is that this set is sigma 1,1 complete. So it's not arithmetic. Right? I mean, it's even. I mean, there's, I guess if you heard this talk before, but I'm re-experiencing it again, right? There's two things to show that this set is complicated and to also show that it's simple, right? Because it's not clear, right? That this should be a sigma 1,1 set, not sigma finite says there's no partition into countably many pieces such that something happens. Right? Why is that existential? Right? Okay, so there's a hint at it, which comes from thinking about a more familiar situation. The second exercise, the set of indices for pi01 subsets of the Cantor set such that C is uncountable is a sigma 1,1 complete set, right? So why is it sigma 1,1? That's Cantor's theorem, right? An uncountable set, a closed set is uncountable if and only if it has a perfect subset. Perfect subset is given by paths through a tree, right? So how do you say that C is uncountable? You have to say that there exists a code for a perfect tree, right? All of whose elements belong to the closed set. Okay, so that's an existential statement, right? And okay, so that's the proof that it's sigma 1,1. The proof that it's complete is it is an exercise. You got to do something. Okay, but it's interesting from a couple points of view. First, I never thought of Cantor's theorem as giving an optimal index set calculation, right? But it does. Right? And the second thing that's interesting is you think about the analysis of trying to see what's the pi1. If you have a pi1,1 situation, right? Being in the set corresponds to something's well-founded. Right? That means that you should, when you analyze something that's pi1,1 complete, right? The analysis should involve coming up with a natural rank. Right? Why is this? Why is the pi1,1 statement true? Well, it's true at step alpha, right? Because the situation invokes rank alpha. Okay, so that's clear in the Cantor-Bendixson theorem, right? That there's the derivative, and you keep throwing away isolated points, and then at some points you've either got a perfect set or you've thrown everything away. So that for a countable set, there is a ordinal at which you throw everything away. Okay? That's the natural rank. Now, what's involved in analyzing that situation? You have to work your way up the hype hierarchy. So the objects that you're looking at are becoming more and more complicated, arbitrarily high in the hype hierarchy. Right? So the analysis of the phenomena involves looking inside at hyperarithmetic objects. If you're going to discover that C is countable, where's the counting going to show up? It shows up at some recursive ordinal. See the light face pi01 set. Okay, so yeah, that's a bit more complicated than just looking at something arithmetic. Right? You have to look, the objects that you have to run C against are arbitrarily high in the hype hierarchy. Okay, so the ingredients of Davy's theorem about analytic sets which are not sigma finite have non-sigma finite closed subsets. It's a similar situation as in Cantor's theorem. What Davies did was show that if C is not sigma finite in our case for linear measure, then there's a perfect tree of closed sets, not a perfect tree of paths, a perfect tree such that each path corresponds to a closed set, each of positive measure. Okay, so that gives you an existence, right? An existence that makes it sigma 1, 1. And the fact that it's sigma 1, 1 hard is like the exercise, right? It's yes. Sorry, I should have said that. A tree of closed subsets of C. Thanks. Okay, so that's the way this thing works. So you can see just for these very simple objects, pi01 classes, understanding what is sigma finite or not sigma finite is a lot more complicated than understanding what is null or positive measure. Right? So the problem of trying to characterize non-sigma finiteness has to involve ingredients that go beyond some sort of alternation of arithmetic quantifiers. Yeah. And it's well, to see that it's not sigma finite, right? You have to exhibit some kind of, well, the description of the tree is countable, but it's the paths, this disjoint subsets of non-zero measure. Yeah, each path corresponds to a like the Cantor construction. You have a tree of perfect closed subsets that they all have positive measure and they're disjoint. Right, and different paths correspond to just the characteristic function of each path. Each path is continuously associated with a tree whose paths are the elements of the closed set. Right, and disjoint, correct. Okay, so the way that this fills in what it means to be not sigma finite, it's exactly this kind of existence of perfect trees of pairwise disjoint closed subsets of positive measure that show up in showing that this thing has non-sigma finite measure and the set of Liouville numbers are not sigma finite for the gauge functions that were already described. So that's once you know sort of the complexity of the optimal complexity of some situation, you can try to use the ingredients that go into it, right? To instantiate, sort of. There's some work to do. Okay, and with that, end my talk. Thanks.
Questions? Yes. Let me move the mic around.
So what you were using towards the end is that basically if you can't partition it into countably many parts, that make it finite, and actually have to be continuously many disjoint pieces
to make it not zero. Correct.
Yeah. Is there any niceness aspect involved in making that happen, or is sort of the like minimum cardinality of finite measure pieces that you need in order to partition something, is that sort of just naturally not an intermediate cardinal?
Yeah, the proof goes by finding a perfect set. So it's trying to find it by some kind of recursion of size, build it up by recursion. You can do it that way, but the natural proof is to do this. It's interesting to see. So this is Davies. We're getting leverage out of Davies' argument, just like we could get leverage out of the Cantor-Bennigsen argument. The ingredient, the way that Davies' proof is particularly artful, right? And the way that and it's not that often that you see arguments outside of logic where there's some kind of proof where suddenly arbitrarily high in the hype hierarchy comes some kind of ingredient. You do this construction, you set things up, and then pop, right? Everything goes well until pop, something happened, right? But that thing that happened is arbitrarily complicated in the sense of hype. That's how the argument goes. But it really is a precursor to the kind of arguments that we're accustomed to. Yeah, so you can't. They're not particularly nice sets because they sort of get exposed arbitrarily high in the hype hierarchy. I don't know. That's about the best I can do.
Regarding the question you had about sets of dimension D that are not sigma finite for HD, I was thinking, would it be enough if you have examples where you have the exact gauge function, like a function for which the measure is finite but positive, and then
I tried to look for that. I tried to look for examples where you could find naturally occurring sets for each gauge function, and I couldn't find it. If that's what you're asking.
Yeah, so I think, for example, for the level set for the Brownian motion, there is some exact gauge function, like there will be so like the dimension is 1/2, but the exact gauge function is something like square root of t times something involving the log. And
no, I think it's I think Brownian motion, like I said, this orders in Perez. They have several examples of things that have exact gauge dimensions, which are not given by power functions.
But would that imply that it's not sigma finite for h 1/2 because because if this exact gauge function is like strictly to the left or the right, I forgot. Then if it's if the set is finite for h,
correct.
Yeah.
Yes.
So
you're
that
right.
would be an
That's
example.
Right. Yes,
Okay.
those are good. Yeah, you're right. I didn't think of doing that, but you're right.
Thanks.
Any more questions? Any questions online?
That you were using the sequences with dimension D points. Is there anything useful that comes out of taking the relativizations of it? I mean, they all have the same property, but
I think I was thinking about, actually, that's nice. When I was thinking about this, the closer you get to the talk, the more you think about it. The issue of what is it that makes, I think that there is the possibility of a nice insight into these into these kinds of things. What is it that gives a set size as measured at a gauge function? Right? And I think that it could be that there may, even though the closed sets, and the sizes of the closed subsets, they can't do the job by Besekovich's theorem, right? And similarly, Frostman's lemma, that this being the support of a certain kind of measure, well, those measures are all capacitable, right? So those also can't give an exact explanation of what supports the size of a set. I think that there may be some way to express it in terms of complexity theoretic notions. When is a set large? So we have some explanation for when does a set of dimension D in terms of complexity theoretic notions. Right? But it may be that the only way to give a cogent explanation in view of the classical results is to just change the paradigm. You don't fill it out by closed sets, you fill it out by some kind of information theoretically determined subset. It's large because the largeness is supported by some kind of complexity theoretic property. But I don't know exactly what that property is, right? And it can't be the ones that we've already identified because those are all analytic. Right. So there's an interesting test problem there. And relativization or quantifying over relativized things may hold the trick. I don't know what it is.
Any more questions? All right, let's thank Ted once more.
Thanks.
So, thanks everybody for the day's talks. They're awesome. We'll see everybody tomorrow.